Hello and welcome to another video in this series about object-oriented programming. In this Under the Hood video about class members, so the static variables, I'll demonstrate what the effect is in memory when static variables are declared and the difference with non-static or instance variables. This is the rectangle class displaying some of the class member variables, so the statics, as implemented in the hands-on video. First, I declare some static final variables, which are used during construction and validation in the setters, which are not displayed here. Second, I introduced a count variable, enabling us to count the amount of instances of rectangle. The variable is public for now, but should be encapsulated. That will happen in the next version. What I'm going to focus on in this video is how static compares to non-static behavior. In other words, class versus instance members. But before that, let's have a look in memory what static behavior looks like at runtime. And I'll do that by executing this client code step by step in the next slides. What is this code about? So it uses the rectangle class as just displayed. First of all, printing one static final variable height, which will be 10. Then we print the count variable. Since no object has been created yet, the count will be 0. Then two rectangle objects are created and printed out. The first one using the default constructor and the second one using the 4parameters constructor. And then finally we print the count again and we'll see the variable of 2 rects. Let's dive under the hood now and explore what happens in memory when we execute this client code. So what happens when we execute the first statement, printf of minimum height? The new thing in memory when we use class members is that there will be some kind of static area reserved in memory where all the static variables will be allocated. Objects, when created, are allocated on the heap when a new instance is created using the new keywords, but static variables are allocated from the moment something of the rectangle class in this case is used for the first time, because that is a time that the runtime will load the class in memory and initialize the class variables. This printf statement uses the minimum height static class member variable of the rectangle class. Since this is the first time something of the rectangle class is being used at runtime, will all the static variables belonging to the class be allocated in the static area. That involves, I don't display them all, the minimum x, y, height, width, and the maximums I use in a hands-on video. All of them are allocated in a static area and only once, not per object, as you see in a minute, plus the count variable. They are all of type integer and their default value is 0 unless assigned a different value when declared. Minimum height in our case is assigned value 10, so that's the value that gets filled in memory. The count variable, though, I didn't assign any explicit value to the count initially, so its default value is 0. Okay, so when we print the statement, we see minimum height is 10 in the outputs. The next line is a print of the count. Well, we clearly see that the default value is 0, so in the outputs the value of 0 is displayed. Just a note about the name given to that area in memory, the static area. Now, class variables used to be allocated in the method area. Some seem to say that it is logically part of the heap, so as specifications seem to change, and I don't want to pin an exact name on the area where they are allocated, I'll refer to it as the static area. But never mind the exact name of the area, what I want to demonstrate here is that class variables are not part of an object. Then creating a rectangle object using the default constructor, which we can split in 3 parts. First of all, the declaration of the local variable rect1, which will be allocated on the stack. Then the creation of the object using the new keywords allocates our object, so space for our 4 instance variables or non-static variables, x, y, height and width with a default value of 0, after which the constructor code will be executed. And as we saw in the hands-on video, when the default constructor is invoked, the setters are receiving the values of 0 for x and y and 10 for height and width. So that's for creation and initialization of the rectangle object. And since a new object is being created and there's a constructor being invoked, the count variable is increased by 1. After which the assignment takes place and rect1 is now referring to our initialized object. Note that the count variable is not a member of our objects, and that due to the keyword static. Class members are not a part of an object. Then if we print it out, I just denoted it like this to save some space, and what we see are the values of 0 for x and y and 10 for height and width. Then the creation of our second object, passing 4 arguments to the 4 parameters constructor. First of all, allocation of the local variable on the stack. New will allocate our object on the heap, and again, only the instance variables are part of the object, x, y, height and width. The constructor being invoked will make sure that the setters will receive the values of 10 for x, 20 for y, 100 for height and 200 for width. And again, since a new object is being created, our count variable is increased. Creation and initialization of the object complete. We assign and rect2 refers to our second object. Then we print the second object and we see the values of 10, 20, 100 and 200. And finally we execute the print of this rectangle count again. Just by looking at the value in memory, can we predict that the output will be 2. Okay, so this for class member variables. Note where they are allocated. Class member variables are not part of the objects, which is good because we only need one count. Let's now compare static with non-static behavior. In other words, class versus instance member variables. And I'll explain it with the count variable, which is now a class member, since declared static. But why did we make count static? Well, ask yourself, does count describe a characteristic of a rectangle? And the answer is no, because count is not an intrinsic property of rectangle, as are x, y, height and width. In other words, you don't need count in order to draw a rectangle. As just demonstrated in memory, count is not related to rectangle objects. So we don't need a counter per object. Instead, we just need one global counter per class. Now let's remove the static and see what happens when we make it an instance member. The first line will be exactly the same, so printf rectangle min height. But what happens in memory is a bit different, because since count is not a class member anymore, it will not be allocated in this static area. Only the remaining static variables, those static finals like minimum x, y, height and width, but not the count, because it's not a class member anymore. So when printing min heights, we have the value of 10 the same. Now we cannot print a count anymore, because since now behaving as an instance member, we need an object first before we can access it. We create our first object as before, so rect1 on the stack. The new allocates our object on the heap, and now note the addition of the count variable because it is a instance member, and so it's part of the object, as are x, y, height and width. Now the structure of the object in memory reflects the declaration order of the instance members in a class. Here I draw the count variable underneath the last instance variable width, and this will be the case if count has indeed been defined as last instance member in the class, so below the 4 other instance variables x, y, height and width. This is unlike in the hands-on video, where I temporarily declare count above the other instance members, in which case I should draw count here on top of x, y, height and width. Anyway, wherever count is declared, what is important to remember is that count, if declared as instance member, will be part of every object. The constructor initializing the values for x, y, height and width through its setter, and then count will be increased for this object to 1. Then assigning rect1, and rect1 refers to our first object. When printed out, I didn't change it to string implementation, so I'm not printing out the count variable. I do that differently in a second. So the output is the same on screen, but note that internally our object has one additional count field. Then the second object, very similar, rect2, our object, and so again, the structure of the object is all the instance variables, including count. So every object will have its own count variable. The setters will initialize x, y, height, and width, and for this object will the count be incremented. Then the assignment of rect2, printing out same output as before, because I don't print the count on the screen. I'll do that using this line, as said, because count is for now public. The client can access it, but needs an object reference, rect1 and rect2. So I'm just printing out the two values. Well, they are both 1 just by looking at the structure of the object, and this is what we get in the output. And this is not the behavior we want for a counter of a class. If the counter is supposed to count the amount of instances of a class, then we don't need a count field per object, but one global counter as displayed in the previous scenario. So count must be static. So count must be a class member. Okay, that's for this video. I hope that you get a better understanding of the behavior of class versus instance member variables. If you like this video, thank you for pressing the like button or subscribing to my channel. See you in the next version of this series. Bye bye.